So without further ado, today's webinar is going to be based around the ultrasound use with case studies in the field, looking at the applications and other areas where we use technology and what they have found. So first of all, we will cover obviously who we are. We'll go over a little bit about how ultrasound actually works and where we can use it. And then we'll go into the examples based around the ultrasound technology in those application areas. So yeah, first of all, for those of you that maybe don't know who we are, let's go over who UE Systems are first of all. UE Systems are manufacturers of ultrasound instruments, providing hardware, equipment, training, and ongoing support with our users in industry all around the world. Our main headquarters is based out of North America, with many regional offices in the Americas itself. Here we are based out of our European headquarters in the Netherlands, with many regional offices all around Europe as well. We also have offices in India, the Middle East and Africa, Asia, and also partners in Australia too. So we do have quite a wide reach when it comes to providing ultrasound solutions to our customers. For those of you that are obviously in the UK and Ireland side of the world, my name is Christopher Hallum. I'm the operations manager for UE Systems. I've been here with UE now just over 8 years. Started originally as a trainer with UE, going around teaching the technology and evolving over time to looking after the operations of Northern Europe now. My background is in electrical engineering from the military, and also a qualified teacher as well. So have lots of experience in teaching users, teaching people engineering principles and everything else. And over the years, we've also managed to grow the UK and Ireland team with our head trainer, Craig Armstrong, Daniel Lambourne in the UK as well, providing training and support to our users. And recently joining the team, Terry Ruddick in the team as well, providing support to our users in the field too. So the capacity to provide that reach and need for support is very key with these technologies. So we have a very good team ready to help those users in the field. So ultrasound as a technology, what is it? How does it work? There are different types of ultrasound technology out there. A lot of people will be familiar with the pulse echo side of things, where we have ultrasound devices that transmit and receive ultrasound signals. You might see those in the medical industry, also in NDT practices for detection of cracks in welds and things like that. You also have the power side of ultrasound, which looks at things like cleaning baths, welding and cutting equipment that's vibrating at high frequencies. Where the ultrasound technology that we manufacture falls into is the airborne and structure-borne ultrasound, where we're listening for ultrasound emissions generated in the environment that we are in. So ultrasound itself, as human beings, we can normally hear in the frequency range of 20 hertz to 20 kilohertz. And this audible sound is generated through changes in pressure that we pick up in the air through waves that we actually then transpose in our brain to see what we think is actually sound. With ultrasound is generated in the frequency range of 20 kilohertz and beyond, way outside of our human hearing range. Now, the differences are here where ultrasound generated is more directional. It's highly reflective. So when we're using ultrasound devices, as we scan towards the source of a sound, we hear it. As we move away, we lose it. So it helps us to identify where the emission is coming from. The two ways in which ultrasound is generated is through turbulence. So think about pressurized pipework with a leak, creating turbulence will create ultrasound, and also friction. So think about a rotating asset that generates friction, for example, in a bearing, that also generates ultrasound. And we can pick those up in the airborne medium and also in the structure-borne medium using contact modules. So ultrasound itself is a very versatile piece of equipment. It's not a one-trick pony, you could say. It's not it's more of a jack of all trades sort of technology that can be complementary with other technologies in the condition monitoring world. So applications that we can use the technology for: condition-based lubrication, helping us listen to the friction as we're lubricating our bearings. Using it then to go into bearing condition monitoring that helps us identify early stage failure of a bearing. Leak detection, one of our earliest applications and most widely used applications for identifying the turbulent flow of any leaks. We can also use it for steam trap testing and valve testing for leakage and correct operation. And finally, for partial discharge detection, looking for any identifiable electrical emissions generated from early stage failures. So let's go into these applications one by one and look at some case studies as well while we're there. So from the bearing condition monitoring front of it, again, one of the larger applications that our users use the technology for, we can use it to provide early warning of bearing failure, and it can also be used on slow speed applications to help us identify early stage problems. With bearing inspections with ultrasound, we're picking up the friction, and the change in friction is one of the earliest changes of the condition of a bearing. Before a failure is even in its processes, we can identify a change in the lubrication level because of the rise in friction that can help us use ultrasound to correctly lubricate, for example, and keep that bearing at its most healthy spot. It doesn't mean to say that if you identify a rise in friction that there is an imminent failure occurring. It's a flag that you could then use to identify something is changing. And then you may want to inspect more frequently to see if that change occurs more rapidly. What we do with ultrasound and bearing inspections is set baselines. Set baseline values, we then monitor and set up simple alert levels. Now, depending on whatever the baseline value is, 8 decibels above the baseline can identify a potential lack of lubrication. When we get to 16 decibels above the baseline, this can indicate early stage damage being occurred to the bearing. And if we get to the point where we're at 35 decibels above the baseline or more, then chances are you're probably going to hear it already audibly, but this would identify a bearing that is in very late stage of potential failure. And what does that look like ultrasonically? So just for an example here is sort of a plot chart of the rise in friction of a bearing over time. We see it rise, we may hit an alarm level where we could then lubricate the bearing, hopefully reducing the friction back to where it should be. But over time, that friction is going to rise, and it's going to get to a point where things like performing lubrication is not going to affect the overall friction and identify a failure that we need to then rectify. So I want to give an example. Our first example is a very simple one where a user has a planetary gearbox. And this was from a user in the field that we supported that had a problem with a refurbished planetary gearbox. It was a slow speed application, but also with ultrasound, it's understanding the asset's operation itself is also key to knowing what we're listening for. Now, as we know the operation of a planetary gearbox, what we would expect to hear is a smooth modulating sound as each of the planet gears moves past the sensor where it's placed on the housing. Now, with this recording, the user identified what they thought was an unusual sound that didn't quite sound right to them for something that had been recently refurbished. I'm going to play the sound now, and hopefully you can hear this. So from that sound there, you can hear a modulating sound, but you can also hear it sounding quite coarse, a crunching sort of sound. Now, this is something that was not what we would expect to hear. So as we identified this, the next check was to make sure that the oil was inspected. So the oil was inspected. It was found that the oil was very blackened. And we suspected that actually the type of oil that was supplied to this gearbox was actually the incorrect one. They did some further research and found that it was correct, that the oil was the incorrect type. So rectification action was taken. We then put the correct oil into the gearbox and we retook our readings. And this is what it sounded like just after changing the oil. We can see that just a change in the right oil produced a much smoother, uniform sound. We could still hear the slight modulation, but now it sounded much smoother. So in this instance, we avoided any further damage being caused. But just to highlight the sensitivity of ultrasound, we can identify even an incorrect type of oil being placed within an asset to show those sort of early stage problems that we can avoid. The next one was actually identified while on a demonstration at a corrugated card manufacturer. Sometimes, we find these things while doing demonstrations because UE Systems are not a service provider. So we rely on our case studies when identifying either on demonstrations or through our users sharing their finds with us. So just a standard gearbox. And with this, if it's all working very well, should be smooth and uniform in nature. The first gearbox we came to on this visit sounded a little bit like this. So we can hear that repetitive impacting sound that actually identifies damage to one of the gear mesh within the actual gearbox itself. Even when you've got damaged teeth in there, you're going to hear impacting or increases in friction, and it's going to be repetitive. And if we know what stages we're at and the speeds that they're running at, we could actually identify what gear mesh could actually be at fault here. When comparing that to another similar like for like gearbox, we can hear what we should sound like. Smooth and uniform in nature. This is what we should see. So the gearbox in question at the time, as part of the demonstration, was left to run. A few months later, I questioned how things were going with that gearbox. And at the time, they told me that that gearbox was out for overhaul because it failed. So again, identifying something is one thing. Doing the corrective actions early enough is the other side of things that we need to make sure that we do. Ultrasound is also very good when it comes to slow speed applications. We can use it on very slow speed bearings because if we have rotation, we have friction. We just have to adjust our frequency of which we're monitoring and listening at to help us identify what's going on. This was one that was done again during a demonstration on site, large scale oven dryer kiln, relatively new asset, was only a few months old. And we had no historical data on this or anything. It was just a demonstration. But what we did have was 8 bearings on this asset that were all like for like. So they were the same speed, they were the same load, same type, roughly rotating at approximately 7 RPM. So what we could do is take readings of each of the bearings and compare them. So out of the 8 bearings that we monitored, we registered a 0 decibel value on the unit, but we could still hear the sound in the headphones. So we could perform sound recordings to help us identify any anomalies. It's very important when doing slow speed bearing monitoring to take into account the tonal quality of the bearing emission as well as the decibel value, because the 8, 16, 32 decibel values for regular speed bearings is slightly different when it comes to slow speed applications. In this instance, we could see that actually one bearing was registering 2 decibels, apart from the rest being at 0. The first 7 bearings sounded like this. Smooth and uniform in nature, very low level emission, but that is what we would expect to hear of a relatively new asset at slow speed bearing levels. But like I said, one of the bearings registered 2 decibels, which actually is a 200% increase compared to the rest. And in the headphones, there was a very, very faint ticking noise occurring. So we performed the sound recording again, and we then played it back. And this is what it sounded like. So even to the untrained ear, if I had 8 bearings that were like for like, 7 of them looked like the trace on the top and 1 looked like the trace on the bottom, I would definitely consider that something wasn't right with this bearing. Another way to help us with identifying the problem was taking things like grease samples. And within the grease sample, there were metal particles identified. Now, to replace a bearing of this size on an asset of this size is going to take some considerable time. And if failed during operation, would cost a lot of money and downtime as well. So with this being identified, the user then scheduled the corrective maintenance to be put into place. And once they took the system apart, they shared the images with us. And as we can see from the images on the screen, there was some severe levels of damage occurring to this bearing. Part of the outer race had fallen off as they dismantled it. And we can also see in the middle picture and the one on the right that the cage has been damaged and one of the rolling elements is now at 90 degrees to where it should be. And you could see that on the trace on the sound recording where that rolling element was now sliding over the cracks and not impacting them as it rolled past. So again, this is helping identify a problem before it became a serious problem. So another example of a more traditional motor, you could say, again, during a demonstration, looking at a couple of motors that were driving pumps that were like for like. So some simple recordings were taken of the drive end bearings, just to do a simple comparison. As we can see from the image, we were getting an amplitude of 29 decibels, and it sounded a little bit like this. A pretty smooth and uniform sound. I believe that this could have been reduced in amplitude if lubrication was added to this as well to help improve the signal a bit more. But in general, this was a bearing that didn't sound too bad. The one next to it, we took a reading of, and the same point gave us a decibel value of 61 decibels. So same operating conditions. So the level of rise in decibel value is quite significant. And the tonal quality on this one was also very different to the first one. And it sounded like this. The tonal quality sounds very poor. The decibel value is very high, and this bearing was identifying pretty significant damage to it. Again, this was just part of a demonstration, so I recommended to the users on site to maybe look into this motor a bit further. The feedback I got afterwards was that when they took it apart, the bearing had almost disintegrated and had fallen out of its housing. It was quite a significant problem there. But again, we identified it just at the spur of the moment while doing that demonstration. Another example of how we can use simple comparison methods to identify problems. So here's another one given to us by an experienced user, drive end motor bearings in a pharmaceutical plant that had been using ultrasound for some time. They used the DMS software to create their routes and collect their data over a period of time. They were able to set their baselines and set steady frequencies of taking readings. But as you can see from the trace, the ultrasound level started to rise over a period of time. They started to lubricate the bearing when it hit its first alarm level, which reduced the value a little bit, but not quite to the baseline. And then after that reading, we saw continual rises in the ultrasound emission. Fortunately, again, ultrasound is a very early detector of these problems. So they could schedule the downtime, make the necessary work orders to be raised, and make the corrective actions. So that's bearing monitoring. Going on to condition-based lubrication now, because all we're doing here is measuring the friction level of the bearing to identify those early changes. And if we can identify an early change in condition at this earliest stage, we can then provide the correct lubrication to make sure that we avoid this bearings getting any worse or actually going into a failure mode themselves. So when bearings do fail prematurely, normally it's some sort of lubrication related issue that's caused that problem, whether that's contamination, either unsuitable lubricant, mixing them, going long periods of time without greasing, or actually not putting greasing in at all. And I can imagine a lot of people that are present on this webinar today have experienced all of these, if not some of them more than others. But it's something to think about. If we can actually improve the standard of lubrication in our bearings, we will significantly improve the lifespan of our bearings and our assets. So the good thing about using ultrasound is, again, like I say, monitoring the friction level. If we can catch that rise at an earlier stage and provide grease at an earlier point, we can avoid that increase in excessive friction that can actually cause damage to the bearing. So we're moving away here from a time-based lubrication program to a time-based condition monitoring program instead, looking at the data, letting the bearing tell us when it needs the grease. And when we do apply that grease, we can use the ultrasound to listen to the bearing and apply the correct amount. So it removes that guesswork. Most time-based lubrication programs will be a certain frequency of time or running hours and a certain amount. And my question is that the right amount? How do we know that's the right amount? Using ultrasound helps us understand what the bearing actually needs. So what we would find is that as we lubricate a bearing, if a bearing requires grease, we will see that amplitude of ultrasound reduce significantly. And what we do is we apply the grease until the decibel value goes no lower. Give you a little example here of video, and it has a 2-factor example on here, and I'll explain it afterwards. So first things first, when we lubricate a bearing, we want to actually apply grease slowly and steadily. I would quite happily say that the gentleman in the video was quite keen to get that grease into that bearing and was going a lot quicker than I would expect. But what we did see is that the decibel value went from around 57 decibels down to 43. And what we also do is once the value doesn't go any lower, we stop. Because if we see the decibel value then begin to rise, that's a sign of them over lubrication. So again, in this instance, we ended at 47. So more grease was applied than necessary in this instance, and just gives us an example there of what not to do as well at times. So this, slide actually goes over exactly what I just said, slowly, step by step. At times, it might take a little while for the grease to actually hit the bearing, depending on the length of the grease line. The amount of times that I've gone around some bearings with remote lines and the user has said, we grease this regularly and we're putting several shots of grease in until nothing happens. And then one more shot of grease and all of a sudden it drops, tells us that the grease line was empty. So like I said, what we do is we grease the bearing until the friction level goes no lower. If the friction level starts to increase and the decibel value rises, we stop. So the next sound file is actually an example of a bearing requiring grease, but then the user at the time is going to then continue greasing the bearing to see what happens as we over lubricate. So as we can hear from that sound recording and the traces on the screen now, the friction level was quite high initially. When the grease started hitting the bearing, we could see it drop dramatically. And that's where normally the user would stop. But in this instance, the user carried on to grease, and we can see the gradual rise in friction again as we over lubricate the bearing. So this is an example of, the right procedures at the start, but the second part is when we're over lubricating. So it helps us to understand what actually does happen when we over lubricate a bearing. So going on to another application, another one of the common applications that people use ultrasound for is leak detection, helping us, find leaks quicker, saving costs sooner. So if we think about our compressors and the cost of a compressor over a 10-year lifespan, we can see that one of the largest contributors to that overall cost is actually in energy usage. And if we think about all of that energy usage, on average, 30% of that energy is actually wasted through leaks. So it's one of the areas where users of ultrasound can find quick wins by identifying their leaks and then repairing them, because it's great to find the leaks and report on them, but until you repair them, they're still costing money. And especially in the current climate where we see energy prices fluctuating, rising, and things like that, it's really important to actually keep on top of these, because if we don't repair our leaks, then we're going to add added pressure onto our compressors and reduce the lifespan of our compressors too. So things to consider when using ultrasound for leak detection with the Ultraprobes is that the fact of the matter is that turbulence is what generates the ultrasound. So turbulent leaks create the ultrasound. We do have instances where there are leaks that produce laminar flow, and that laminar flow does not produce ultrasound. But these leaks are normally few and far between, depending on the type of medium that it is and the pressure behind that. But again, ultrasound is very directional, so we can identify where it's coming from. We can actually then quantify those leaks too. And we can detect low pressure leaks as well, and quite small ones. Ultrasound is highly sensitive. There's also a different way of using ultrasound to help us identify leaks. Whereas the Ultraprobe would use the sound through headphones, we have ultrasonic cameras that can help you identify the leak as an image on the screen. Using ultrasonic cameras can improve the speed with which we can identify our leaks. It can help us then with reporting and identifying where they're coming from. So it's easier to pass on those work orders to users to then make the necessary repairs. It's pretty simple to use, requires very little training, and can give you a quick return on investment as well. So in this instance, we have a technology that can help us with hearing the leaks. An example of this video I will play now. A very simple method using the gross to fine method to identify the source of the leak using the directional properties of the ultrasound being generated. The other way, by using the camera, is to help us see where the leak is coming from. And you'll see what I mean by it speeds up the process. A nice simple hotspot that can identify the source of the ultrasound. Again, speeding things up. More visual sometimes is much more easier. With the Ultraprobes, there are also apps that we can use to help us record our leaks, report them, and show the costs as well. And these same apps are built into the ultrasonic camera, so the camera is also producing these reports as you go along too. Very visual, very good at explaining it to other users to show the potential costs, giving us our total overall cost of the leak survey, individual costs of each of the leaks, along with qualifying them as minor, moderate, or major leaks as well. So we can then use these reports to make the necessary repairs and also have the report to show us how much we have saved as we make the repairs. So a bit of an example here was one well done during a demonstration to demonstrate an example case study of a leak. A leak is a leak, and it sounds just like a leak in the ultrasound spectrum like it would in the audible spectrum. But this was an automotive plant, and I think I spent maybe half an hour or so just identifying leaks. Unfortunately for this plant, they had a lot of leaks. So finding them wasn't a problem. And as you can see, in just a short time, we identified over £41,000 worth of leaks. And so if the necessary actions were taken, you would quite quickly see an improvement on site here. It's one of those things where users on sites and people on sites will get used to their environment. And if you have lots of air leaks going on, that sound will just be normal to some people. To others going in there, you might think, wow, there's lots of leaks here, just like I thought about this plant. But to everybody else there, it was the normal operating environment to them. So once we identified this, some eyes were rolling a little bit and some changes were getting made straight away. So going to the ultrasonic camera side of things, and with ultrasound in general, it's not just compressed air leaks that we can identify. If we think about compressed gases, think about vacuum or false air, or things from a distance, they all produce turbulence that produces ultrasound. So we can use it for specialty gases. So a very small argon leak there on a canister. The next one is false air. So this is in a cement plant where we have false air ingress to an asset. In this video, you can see how the false air and the vacuum leak there is pulsing, producing that turbulent flow on around that seal. And then also from a distance, using ultrasound from a great distance with the cameras can help us identify leaks that would be maybe out of reach. So a few good examples there of what a leak would look like. So another application that we go into now is steam traps and valve inspections. So we can use ultrasound to help us identify leaking valves, but also the correct operation of steam traps too. Now, with steam systems, it doesn't matter what sort of fuel is used, the amount of energy required to generate steam is quite large. And it's always a challenge to keep a steam system as efficient as possible. And, it's always looking at ways to find its way to cool down as such. And we have assets like steam traps in place to help us remove that cooling process, in turn helping to keep the system as efficient as possible. But if we start having faulty steam traps in a system, we can lose as much efficiency as 33% in faulty traps. So identifying them will actually help us improve our energy costs as well. Think of it like leak detection as part of our green sort of efficiencies as such, and finding ways to make savings, reduce our carbon footprint, the amount of energy that we're using. So for those of you that don't know, steam traps are designed to remove the condensate from the system that helps speed up the process of the cooling, but also risks things like water hammer. It also vents air and keeps the system running as efficient as possible. And if these steam traps start to fail, we then start to see these reductions in efficiencies. So there are different types of steam traps out there. And again, this is one of those areas where we need to think about understanding how an offset operates so we understand what we expect to hear. The first example was during a training in a pharmaceutical where we listened to some thermodynamic disc traps. These traps are on-off traps that will give us a rise in turbulence as we start to flush out the condensate, and then a massive reduction in turbulence as it closes again. A thermodynamic disc trap should cycle 2 to 10 times per minute when operating correctly. So here is the first example of one of the steam traps we inspected. So as we can hear there is 2 rises in turbulence, and that's where the trap is opening and closing. And we can see that we have 2 modulations in the space of 20 seconds. So spread that across 1 minute, and we can see that this steam trap is working correctly. One of the ways in which these sort of steam traps start to fail is that the disc on the top of the trap will start to wear, so it won't make a perfect seal. So it starts to cycle more frequently. So we can identify a trap that is still working to an extent, but now showing signs of reduction in its efficiency and early stages of failure. So if we identify those sort of things early enough, we can then schedule the repairs, the replacements, and make sure that we get another trap in that's working efficiently. Because here is another trap in the same area with the same function, and this is how it sounded. If we look across this reading of the same duration of 20 seconds, we can see 2, 4, 6, 8 cycles there, and very short cycles. So we can see that this trap is now starting to work inefficiently and is on its way out. So again, we can then schedule the right work actions and get this replaced when the time comes. So a nice example of what a thermodynamic dish trap should sound like, and one that's on its way out. The next steam trap for our case studies is a float and thermostatic trap that is designed as a continuous float trap, a continuous flow trap. So this is dealing with higher levels of condensate and is continuously ejecting condensate from the system. And what we would expect to hear here is a slight modulation in sound. You have different types of float and thermostatics, and in this instance, this was a free float trap. So when we listen for the sound, we expect to hear the modulating of the condensate being ejected, but we may hear impacting sounds from that free float that's knocking against the sides of the actual trap itself. So this is what this trap sounded like. As we can see from the waveform, we see that modulation going up and down. You can also hear in the sound recording that metal on metal impacting, and that's where the float is just floating around on the bed of condensate, knocking against the sides. So it's about listening to what's relevant and what's not relevant and understanding the type of trap that we're inspecting. Now, when most traps go into a failure mode, the majority of failure modes are wide open. They fail open so that the steam continuously passes through. So this is an example now I will play that is of a trap that is in a failed state and it's blowing through, we call it. So we can hear from that there's no modulation. The tonal quality sounds a bit drier as well to my trained ear, but I would expect to see modulation there. That is telling me I have a trap that is faulty. So just like when it comes to leak detection and the leak app, we also have the steam trap app that can help us with identifying faulty traps and putting a cost to them. What we need to know is how much it costs for us to generate a ton of steam on site. And this was given to me by an experienced user in the food sector, identifying all of their traps, punching that into the steam trap app, along with a few other details, and it can then give us a cost. So we can actually put monetary values to our losses when it comes to faulty steam traps. Yes, you may have quite a few faulty steam traps and the system seems to be working fine. I've come across that many times where I've gone around sites and found faulty tags on many traps, and the users say, well, the system's working, it's fine. We're still getting what we want from it. But the energy costs would have risen significantly, and that's one thing they may not have seen. So it is really important to identify your faulty steam traps and get them replaced when you identify them to help keep that efficiency. Because if you don't, it puts more stress on your boiler, that'll reduce the lifespan of your boiler too. Doing valve checks is another simple way of doing testing for leakage. If you have a leaking valve internally, we're going to have a higher level of turbulence just downstream of that. And what we would do is take 2 readings upstream, 2 readings downstream, take the decibel values, and then employ a certain set of rules. So if point C downstream is the highest value, then the valve is leaking. If the decibel values from A across to D start to go down, each of them, then the valve is in a closed position. If the readings are the same throughout points A to D, then the valve is fully open. Sometimes we might find that point D is actually higher, which is the furthest away downstream. And what we would then do is employ point E and move our contact module downstream to find where the highest source of the sound is, because the emission is not coming from the actual valve itself, it's coming from somewhere else. That could be a bend, that could be a partial blockage, it could be damage to the pipe. So on to our next application, looking at electrical inspections, partial discharge, helping us to identify electrical problems safely and efficiently. We can use ultrasound to help us do non-intrusive inspections of electrical equipment. We are putting the users then at a more safer position and helping us as maybe a first point of call check for any anomalies. Ultrasound doesn't replace thermal imaging, it complements it. With thermal imaging, we need to have eyes on the components. So if we don't have windows or anything, we need to open things up, which again, introduces specific risks on these live equipments. A lot of people use the term partial discharge. From that, we're talking about looking for things like corona, tracking, arcing, all things that can have a serious effect on an asset, and if left untreated, can cause very big risks to the property, to the hardware, to people. And what we can do is use ultrasound to identify the source of that. We can analyze it and actually determine what is actually happening here. So we have a few case studies here from some experienced users that I will share with you. So the first one is arcing, provided by an experienced user, and they provide these sound recordings and we support them with helping build their confidence until they are happy with what they're doing. And so using the contact approach, where we can use a contact module to listen on the outside of a cabinet, the user picked up this sound. It's a non-repetitive sound, varying in duration, but they could do a sound recording and take readings. In the FFT, they picked up 50 hertz harmonics, which relates to electrical line frequency, that tells us that the emission they are picking up is actually electrical in nature. They then had things shut down, opened up the cabinet, and you could see by using thermal imaging alongside this, you could identify exactly what the problem was and where it was coming from. So again, a good use of multiple technologies to help you with identifying a problem and sharing that with the end user. The next one is one of my favorite ones that was given to me by a user. And it was part of a service inspection, looking at power distribution within the building. The user would use ultrasound and thermal imaging to be deployed as part of their inspections, initially starting off with an ultrasound scan of the environment to pick up any anomalies. If they pick anything up, they would then investigate the source of that location and use thermal imaging to confirm that. So the user in this instance started to scan the room and picked up this sound. So from this sound recording, you could see that there were 50 hertz harmonics telling us that there was electrical based sound. There was no repetitive anomalies on the time waveform, but they were short in duration and irregular in pattern. They found out where the source was coming from, and it was from some 400-volt cables coming from a transformer. The thermal imaging confirmed the source and the area where it was coming from. And you can see on the image on the left there, the actual physical damage you could see occurring to this cable. The user then went on to turn off the lights and get their phone out and take a video recording. The next bit you're about to see is the video recording of tracking occurring. So this was very interesting because to look at it, it looks like a very small amount of tracking occurring. But as with any electrical fault, this situation could have continued for days, weeks on end and had no change. But then in a couple of hours or in a few minutes, that could have turned into something a lot more serious. So identifying it and reporting on it is very important. We do not trend any sort of electrical discharge, because the people that I know that have identified an electrical problem and then left it to be trended have had some unfortunate consequences afterwards. So we must report on anything that we detect with electrical problems. Another way of actually visualizing ultrasound emissions from the electrical spectrum is using the ultrasound cameras as well, visualizing the electrical anomaly using the UltraView. Again, from a safe distance, no risk to the user, but being able to identify the source of the sound and actually then report on that by using the images as well. So we can see where it's coming from. A very simple method. So in conclusion, ultrasound is a very versatile piece of equipment that can complement many other condition monitoring technologies. We can use it in many areas, from energy savings to condition monitoring. And one of the best areas that I highly recommend people use it for is lubrication, to help us reduce those bearing failures and keep our assets running at the best they can. The training curve on learning how to use ultrasound is relatively short, and having the right support on hand is also important. So yes, here at UE Systems, for a proper successful ultrasound program, what you really need to think about is the right instrument and equipment for the job that you're doing, making sure that you have the right training. Training is very important with any technology to make sure that you implement this program correctly, but also having the right level of support. Support is key, because even after you've been trained, you still need that helping hand from time to time to help build your confidence. So those are the three things that I always promote when it comes to using any technology when we're out in the field. I'd like to thank you all for joining us today. If there are any questions at all, please ask away. You can contact me on the details on the screen, or even visit our website, where we have a very in-depth learning center where you can learn more about the technology too.